Welcome back to Computer Lessons.
So far, we have built the body of our computer, and we have introduced the soul, the operating system. We know that electricity flows through the circuits, and we know that Windows or Mac OS manages the show. But today, I want to ask you a fundamental question. When you take a selfie, when you send a text message, or when you are watching this video right now, what is actually moving through the wires? What is data? If we were to take a microscope and zoom into your hard drive, or zoom into the Wi-Fi signals floating in the air, what would we see? We wouldn't see tiny pictures of your cat. We wouldn't see the letters of your email. We would see just one thing: a switch. A simple, boring switch. Today we are going to learn the alphabet of the digital world. We are going to demystify bits. Bytes and the confusing numbers like gigabytes and terabytes. By the end of this video, you will finally understand why your 100 megabit internet connection doesn't actually download 100 megabytes per second. Let's dive in. Let's start with the smallest atom of information in the universe: the bit. The word bit is actually short for binary digit. As we discussed briefly in our first video, computers operate on electricity. Electricity has two easy-to-measure states. It is either on or it is off. High voltage or low voltage. In computer language, we represent off as a 0 and on as a 1. That is it. That is a bit. It is a single yes or no question. Now imagine I ask you to describe the Mona Lisa, but you can only use a single yes or no. You can't do it. A single bit provides very little information. But what if we add another switch? Now we have 2 bits. We can have 0, 0, 0, 1, 10, or 11. That's 4 possibilities. If we double it again to 4 bits, we have 16 possibilities. And if we go up to 8 switches lined up in a row, now we have 256 different combinations. This specific group of 8 bits is magical. We call this group a byte. Why is a byte so important? Because 8 bits, or 1 byte, is traditionally the amount of space needed to store a single character of text. When you press the letter A on your keyboard, your computer doesn't save an ink drawing of the letter A. It consults a massive dictionary called the ASCII table. It sees that A is the 65th letter. It then converts the number 65 into binary, which is 01000001. That sequence of 8 switches is what is actually burned into your hard drive, or storage device. This applies to everything. Colors, for example. In a digital image, every single pixel is defined by numbers. A little bit of red, a little bit of green, and a little bit of blue. Each of these colors is usually stored in 1 byte. So, when you look at a beautiful 4K wallpaper, you are just looking at millions of bytes, arranged in a grid, telling the monitor which tiny lights to turn on. It is an illusion of reality built entirely on math. Now that we know what a byte is, let's talk about size. We generate massive amounts of data today, so counting in single bytes would be like measuring the distance to the moon in millimeters. We need larger units. First, we have the kilobyte, KB. Technically, kilo means 1,000, so a kilobyte is about 1,000 bytes. This is roughly a simple text file or a very short email. Next up is the megabyte, MB. This is 1 million bytes. To visualize this, think of an MP3 song. An average song is about 3 to 5 megabytes. A high-resolution photo from your smartphone might be 4 to 8 megabytes. Then comes the giant, the gigabyte, GB. 1 billion bytes. This is the standard measurement for movies and video games. A high-definition movie might be 4 gigabytes. A modern video game like Call of Duty? That can be over 100 gigabytes. That is 100 billion groups of 8 switches. And finally, the terabyte, TB, 1 trillion bytes. We use this to measure hard drives. If you have a 1 terabyte drive, you could store roughly 500 hours of HD video or hundreds of thousands of photos. It is an ocean of data. Now, I need you to pay very close attention because I am about to solve a mystery that confuses almost everyone. Have you ever bought an internet package that promised 100 megabits per second? You get home, excited to download a game, but when you look at the download bar, it says you are only getting about 12 megabytes per second. Did the internet company lie to you? Well, not exactly. But they used a marketing trick. Internet speeds are measured in bits, small b. But file sizes are measured in bytes, capital B. Remember the golden rule. There are 8 bits in 1 byte. So if your internet speed is 100 megabits, you have to divide that number by 8 to find out how many megabytes of actual file data you can download in a second. 100 divided by 8 is 12.5. So a 100 megabit connection gives you a maximum of 12.5 megabytes per second. You aren't being cheated, you just have to do the math. Always look at the capitalization. MB is megabit. MB is megabyte. It makes a huge difference. Here is one last quick mystery. You buy a 500 gigabyte SSD, but when you plug it into Windows, it says you only have about 465 gigabytes. Where did the missing 35 gigabytes go? Did it fall out of the box? No. This is a language barrier between humans and computers. Humans count in base 10. For us, kilo means exactly 1,000. But computers count in base 2. For a computer, kilo is actually 2 to the power of 10, which is 1,024. Hard drive manufacturers use the human definition to make the numbers look bigger on the box. They sell you 500 billion bytes and call it 500 gigabytes. But Windows uses the strict computer definition. It divides those bytes by 1,024, again and again. The result? A lower number displayed on your screen. The physical space is exactly the same, only the measuring stick has changed. So, to recap, data is nothing more than billions of switches turning on and off. We group 8 bits to make a byte. We stack bytes to make kilobytes, megabytes, and gigabytes. And we learned that internet speed is measured in bits, while files are measured in bytes. Understanding this DNA of data changes how you see the world. You don't just see a picture anymore, you see the matrix behind it. Now that we understand the language of the machine, it is time to look back. How did we get here? How did we go from room-sized calculators to the supercomputer in your pocket? In the next video, we are going on a time travel adventure. We will meet the fathers and mothers of computing, from Alan Turing to Grace Hopper.
If you learned something new today, smash that like button. Or should I say, set that like bit to 1. Subscribe so you don't miss the history lesson. Thanks for watching.